This video reviews maximum likelihood estimation for the parameter of a Poisson distribution. This material should be pretty familiar to you from your lectures on introductory probability theory earlier in the academic year, but a little review never hurts. If you feel confident that you already understand this material sufficiently well, then you can feel free to skip ahead to the next video. We say that a random variable y follows a Poisson distribution with parameter theta, written y tilde Poisson theta, if the random variable y has the probability mass function f of y theta equals e to the minus theta times theta to the y divided by y factorial, where y has support set 0, 1, 2, and so on, including all of the positive integers. The Poisson distribution is a common model for count data. Examples of count data include things like how many patents a firm has obtained or the number of people who live in a household. To verify that this equation does in fact give us a valid probability mass function, we need to check first of all that it's strictly positive for every value in the support set of y, and that the probability mass function sums to 1 over this set. So let's take a quick look at the first condition. We can see from the formula e raised to any power is positive. Now, y factorial is also positive for the y's in this support set. And theta to the y, well, theta we're actually going to restrict to be a non-negative parameter value. We'll talk more about that in a moment. But theta being non-negative, then theta to the y is certainly going to be positive. So indeed, the probability mass function is always positive. Now, if we look at the right-hand side of this slide, we can see an expression that calculates the sum of that probability mass function over all values y in the support set. We need to check that this indeed equals 1. Notice that e to the minus theta does not involve the variable of summation y. So let's pull it in front of the infinite sum and look at what remains. The sum y goes from 0 to infinity of theta to the y over y factorial. We recognize this as the Taylor series expansion for e to the theta. So we have e to the minus theta multiplied by e to the theta, which equals 1. The Poisson distribution has a number of interesting properties. Two of the most important ones for our purposes are, first, that its expectation is equal to the parameter theta, and second, that its variance is equal to the same thing. Remember a few moments ago I said that we're going to constrain theta to be non-negative. Well, you can see here why that makes sense. If y is a count, then the average of y cannot be negative. And because theta is equal to the mean of this random variable, theta can't be negative either. I'm going to show you right now how to prove that the expectation of a Poisson theta random variable equals theta. On the problem set, you're going to use very similar reasoning to show that the variance is equal to theta as well. By definition, the expected value of a discrete random variable is the sum over the support set of y times the probability mass function evaluated at y. So we'll substitute in the probability mass function for our Poisson random variable, leading to the following expression. Now, notice that the first term in this sum equals 0, because if we plug in 0 for y, the whole thing vanishes. So that means we can actually re-index the sum to start at 1, and it's still exactly the same sum. Now, the next thing I'm going to do is I'm going to pull a factor of theta in front of the sum. Notice that that takes the power on theta within the sum down by 1. It goes from y to y minus 1. Now, the other thing that I'm going to do in this step is I'm going to use the fact that y factorial is a product of y times y minus 1 times y minus 2, and so on all the way down to 1, to cancel out this y in the numerator. When I've done that, what I'm left with is a y minus 1 factorial. Now, if we take a look at this sum, it goes from y equals 1 to infinity, but actually the terms of the sum are expressed as y minus 1. So we could just re-index this to start at 0, and in doing so, we would have to increment the indices inside the sum such that y minus 1 becomes y. It's exactly the same thing. It's just another way of writing it. And when we do that, what do we have? We have the theta out front, and then we have a sum that looks pretty familiar. In fact, it's the sum just above that we showed is equal to 1. Theta times 1 is theta, so we've shown exactly what we set out to. Suppose that we observe a random sample of size n from a Poisson theta distribution, and we would like to estimate the parameter theta using maximum likelihood. Because the data are IID, our likelihood function is just the product of the PMF evaluated at each of the data points yi. Here we're using independence, and we're also using identical distribution. It's much easier in general to work with the log likelihood rather than the likelihood, so we'll just take the logarithm of this product to turn it into a sum. When we do that, we obtain the sum from I equals 1 to n of yi times the log of theta minus the log of y factorial, yi factorial, I should say. And notice that this term with the logarithm of the factorial doesn't actually involve the parameter. So that's not going to play a role when we try to maximize this log likelihood function to obtain the parameter estimate for theta. At the right-hand side of the slide, I do precisely that calculation, differentiating the terms inside of the sum with respect to theta. As I mentioned, the one with the factorial is going to vanish because it doesn't have a theta in it. Yi log theta, when differentiated with respect to theta, just becomes yi over theta, and the minus theta contributes a minus 1. Now, if we take the first order condition, set this derivative equal to 0, we end up with the sum from I equals 1 to n of yi over theta hat minus 1 equals 0. So rearranging this, the sum of minus 1 n times is just minus n. I can bring that to the other side of the equation. Now I can factor out the theta hat, leaving me with a sum from I equals 1 to n of yi. And rearranging one more time to bring the theta hat to the right-hand side, what we obtain is the maximum likelihood estimator for theta is the sample mean, which makes perfect sense because we already saw that theta is in fact the expectation of a Poisson theta random variable.